Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over the reaction quotient as a way of predicting the direction of change to figure out where you are in the reaction and what side of the equilibrium you're on. So let's get into this. So here we have our generic equation, and here's our K expression, and here's our expression for the quotient. And you'll see that they're exactly the same. So what's the difference? So the difference is that you only use the expression for K when you're using the equilibrium concentrations. So if you know the concentrations at equilibrium, then you can plug that in and find out what your equilibrium constant is. But what if you don't know if you're at equilibrium? Or what if you have concentrations that aren't at equilibrium and you want to know, okay, well, which side of the equilibrium am I on? Well, that's where you're going to use your reaction quotient. So exact same expression, you're just putting in concentrations that are probably not going to be at equilibrium. So they could be, but probably not. So what you do is you put the concentrations that you do have at maybe particular points during the reaction, and you see what Q gives you, what your reaction quotient is. And then once you have your reaction quotient, you can compare that to your equilibrium constant. And so, for example, if you calculate your Q, your reaction quotient, from the reaction concentrations that you have, and you find that your reaction quotient is larger than your equilibrium constant, well, what that means is you got to think of this as a ratio of products to reactants. So we know that the quotient, the equilibrium constant, is the concentration of the products on the top and the concentration of reactants on the bottom. So if your quotient is the exact same way. So what that means is if your quotient is larger, that means you have more product on the top and less reactant on the bottom compared to where you would be for the equilibrium constant. So if your Q value is too large, that means in order to get to your K value, you have to decrease the amount of product you have because it's too much. And that means you have to increase the amount of reactant you have because it's too little. So you're going to shift, or your reaction is going to go to in the direction that's going to reduce the amount of product, increase the amount of reactant. So it's going to go towards the left. So if Q is larger than K, then the reaction is going to go to the left, and that means it's going to go towards products. It's going to reduce the amount of product you have in order to get more reactant. And that what's that going to do is that's going to reduce this, and it's going to make Q smaller in order to get to the reaction constant. Once that happens, then you're at equilibrium. If your Q value is smaller than your equilibrium constant, then it's the opposite. So again, looking at here, if Q is smaller than K, that means you've got too much reactant on the denominator side and not enough product on the numerator side. So in order to go in the direction of K and becoming and equaling the equilibrium constant, in order to reach equilibrium, then if Q is less than K, then what's going to happen is you're going to have to decrease the amount of reactant you have, make this smaller, increase the amount of product you have, and by doing so, that'll make Q bigger, and then that'll go in that direction of reaching equilibrium. So in that case, the reaction needs to go to the right, so it's going to have to go in this direction to create more product and lessen the amount of reactant. And if it does that, it'll shrink Q and it'll approach K. And so the third option is if you plug in your values for Q and you find that they equal the equilibrium constant, then you know that the concentrations you have are at equilibrium. And so there's not going to be a shift in one way or the other. Both the forward and reverse reactions are going to be the rates are going to be equal. So here are just three different situations that you could have. So so if you're starting a reaction and you don't have any products, so if you're starting off with zero product, and you have some concentrations of reactant, well, in that in that situation, you're going to have zero for your products, and you're going to end up with zero for your quotient, your reaction quotient. And so obviously, in order to reach your equilibrium, you're going to have to create product. So you can only get a positive value. So obviously, you're going to have to increase product, and then in so doing, you're going to decrease your reactant and to get that positive value. So that's one extreme. The other extreme is if you don't have any reactants, right? So if you don't have any reactants, but you have products, then you've got the other extreme where this is infinite. And so Q is going to be bigger than your K. And so in order to do that, it's going to have to decrease that. And obviously it's going to go in the direction of creating reactant. So it's going to go in that direction there. So these are just two extremes. And then for this third one, what if you have all of your concentrations are 1 molar? Well, that means that all the concentrations are 1 molar. If you put 1 in for everything, you end up getting Q1. So those are just a few of the different extremes and different ways that you can calculate Q, or situations that you could have for your Q value. I hope this is helpful. If you like this video, if you found it educational, please go ahead and like that button, subscribe to my channel, hit that notification bell so you can be notified by other videos I put out. And also put a comment in the comment section and let me know what you think and if you have any questions. Thanks for joining me. Have a great day.